In the last class, we started looking into another complementary device. The first part of the course was concentrating on mostly PMOSFETs, right? And then in the last class, we said that if we invert all the dopings of that constitute a PMOSFET device, we'll get another device which is a complementary device. But in that case, the carriers of transport will be electrons instead of holes, right? So that's essentially the fundamental difference between a NMOSFET and a PMOSFET is concerned. As far as the circuit designer's perspective is concerned, if you are doing device physics, then there is a lot more differences. But we would like to concentrate on the things that we are interested in, right? So as a perspective, from the perspective of a circuit designer, so the stuff that we are interested in are as follows. So let's say I have a PMOSFET device where the substrate is N-type. I put an oxide, I put a metal gate, and here we put P plus layers. This becomes the gate. Let's say this is the source, this is the drain. Again, just a quick revision. What are we doing? We are putting a battery between the gate and the source. And we are also putting a battery between the drain and the source. So the battery between the gate and the source is essentially responsible for creating holes in mobile holes in the channel just underneath the oxide. And now if you apply an electric field between the source and the drain, the carriers will move from the source and the drain, and effectively, which means there will be current flowing through, and the current will flow through this direction through the wire in the battery. And what is so holy about the current? The good thing about this current is I can control this current by changing the gate to source voltage. So the gate to source voltage gives us this electric field, the vertical electric field in the direction as shown from the channel to the gate. So if I make the source to gate voltage 0, for example, that electric field will vanish and no holes in the channel, which means no carrier transport. And that is an extreme case, but in case of a analog applications, right? For example, the MOSFET usages that we have been doing, we saw that it's not a on-off thing per se all the time, right? Because there is a region between having, if I keep on increasing the gate to source voltage or source to gate voltage, the amount of charge in the channel is going to increase, which means that the current is also going to increase. Hence, there is a dependence on VGS or VSG on the current flow. And hence, the equations of our carrier transports are and this is as in saturation. Obviously, to turn the channel on, you need a minimum VSG, should be greater than VTHP to turn on the device. Okay, and obviously we know there are saturation conditions, there are linear conditions. I'm not elaborating on that right now. So now, then we said that, okay, so what happens if we have another device whose body is P-type? I do the same thing. I put an oxide, and then I put a metal. Here, I do a doping of the inverted polarity. That is, here it will be N plus, N plus. And let's say I call this source, I call this drain. So in this case, if we want electrons to, the majority carrier or the body is mostly of P-type, which means everywhere in the body you have holes. And we want to generate a channel which is unique for electrons in this region. right? That's how we are going to control the carrier transport through a vertical field. So if I have to generate an electron there, we have to generate an electron channel there. So naturally, I have to create an electric field in this direction so that it attracts electrons, and we get a region, a thin region, thin sheet of electrons under the channel. So which essentially means that if we have to follow the same nomenclature with respect to PMOS, I'll have to give a positive voltage between the gate and the source, right? So that will create the electrons. And now if I apply positive voltage between the drain and the source, right? So the electron, you have electrons here. So the electrons are going to flow from source to drain, because source, by definition, source is that terminal from which the carriers are getting originated. So, the electrons are going to flow from source to drain, which means the current will flow from drain to source. So the current will be in this direction, right? Current will be in this direction. So, using the same analogy for PMOS, in order to turn on the device, we need a VGS should be greater than some threshold voltage, VTHN, N stands for NMOSFET. This is required to turn the device on. Okay, I have. You have drawn the direction of flow of electrons. Hold on, did I mistake? Yeah, correct. Right. So yeah, so current should be from drain to source inside the device, and electrons are flowing the other direction, source to drain, right? Yes, thank you. So inside the device, current is between drain to source. Thank you, that's correct. So IDS in this case, since the current in the device is between drain to source, so all the polarities are going to flip. So instead of ISD, which was the case in a PMOS device, it will be IDS. Physics of the current flow and everything remains the same. So just that in case of mu P, it will be mu N, which essentially means that we are considering the mobility of electrons. And as one of the facts is the mobility of electrons and the mobility of holes are not same. So as it turns out, the mobility of electrons are, depending on the technology that you are using, it can be at 2x higher than 2x greater than the mobility of holes, which essentially means that for the same geometrical size of the device, you are kind of getting double the current, right? So that's one of the quirks of device physics. It happens. We cannot control. We use it as is. COX kind of remains the same because, again, this is technology dependent. Once you have a device once you are able to make a device which has some minimum thickness of oxide, you would like to stick to that minimum thickness of oxide for both the PMOS and the NMOS, because you can get higher current if COX is higher, right? So that's why generally COX, which is the capacitance per unit area, remains kind of the same for both NMOS and PMOS devices in most technologies. W by L is a designer parameter, which we can change. And inside the bracket, it becomes VGS minus VTHN square, right? So note that there is an ED similarity between both the equations, just that the drain and the source, ISD becomes IDS, VSG becomes VGS. Okay, so before we proceed with the linear region condition, so let me also introduce the symbols for the NMOSFET. For a PMOSFET, the symbol was this. The arrow is always connected to the source terminal, and the direction of the arrow points to the direction of the current flow, right? So similarly, in this case also, we have the same structure. So the arrow is going to point to the point to the arrow is going to be connected to the source terminal. So if I connect, say this to be the source, this should be the drain, this should be the gate, same as case of a PMOS, then the arrow should be connected to the source terminal. That's okay. But what is the direction of current flow?
Towards the source.
Towards the source, right? So the arrow direction flips, it becomes this. And this is kind of awkward to see because normally we are used to seeing current flowing from top to bottom, right? Just like gravity. And so normally this is not how it is drawn. We flip it and put the drain on top, source here, gate here. So this becomes IDS. So that's why you'll see this symbol being used most of the time, not the other way, right? So, but there is no difference between those two symbols. Okay. So now let's get to the other condition, which is the linear region condition. So that is something that you have to be slightly careful about. Argument is still the same. So in this case, source, gate, drain. Gate, source. So what was the argument for linear region condition? The linear region condition used to happen because when we have some channel, when we have channel charges and the source and the drain voltage are not identical, right? When, let's say, the drain voltage is much lower than the source voltage. So we have a battery between source and drain, let's say. So what is going to happen? The concentration of holes towards the drain are going to reduce. And the concentration of holes towards the source is as is. So as you keep on increasing VSD, or as you keep on reducing the drain voltage, the channel charge, instead of being rectangular, would have become something like this. Right? Do you recall? Right? So, and if you keep on increasing VSD, or if you keep on reducing drain voltage, there would have been a pinch off condition. Right? There would have been a pinch off condition, and the pinch off condition was that the sliver of MOSFET around the gate drain junction was getting, I mean, the difference of the gate and the drain voltage was becoming equal to the threshold voltage, right? So that caused the current to saturate. So that was the condition for saturation region condition, right? That was the edge of the saturation to linear region condition. So what is the condition? The condition is the difference between the gate and the drain voltage was becoming threshold voltage, right? So because of that sliver of MOSFET, which is just connected, right? So if you recall again, the argument was the big MOSFET, this big MOSFET, we were looking at it as slivers of small MOSFETs connected adjacent to each other. So the one that is close to the drain side was almost getting turned off. Right? It's not actually getting turned off, but the condition of the channel vanishing appears. And under that condition, we are hitting the saturation region condition. So what is the saturation region condition? It's when the small sliver of MOSFET at the gate drain junction goes from having some channel charge to no charge. Right? So which essentially means that the gate to drain voltage becomes VTHD. So that was the condition. So similarly, in case of a NMOSFET, what will be the condition? If drain to source voltage is same, then I have a rectangular sheet of charge. So now we have the drain voltage. So again, is that under the condition that I am seeing a current flow, would drain voltage be higher than the source voltage, or source voltage be higher than drain voltage? In case of NMOS, the drain voltage will be higher, right? Because again, we are applying a battery between drain and source, right? So if you are not comfortable, go back to this picture on the right. As you see that we are the electrons are coming from the source to drain, which means the current is flowing from drain to source. The drain is at a higher voltage. So in case of an NMOS, so we apply a battery between drain and source. So gate to source voltage remains as is, right? So the battery between gate and source doesn't change. We are cranking up the drain voltage, right? We are increasing the drain voltage. If we increase the drain voltage, naturally, from this condition, the current is supposed to increase. But what's going to happen? What's going to happen to the channel around the around this junction? If I keep on increasing it beyond certain amount. Okay, so maybe that is overcomplicating things. Yeah, so let me repeat. So let's say the threshold voltage for this NMOS device is 1 volt. And note that the threshold voltage in this case is defined as VGS, that value of VGS when we have channel, not pinch off, when we have channel. Threshold voltage is with respect to VGS, right? Threshold voltage is that value of VGS for which we are going to see electrons in the channel, not pinch off. So once we have a battery connected between VGS, which is greater than threshold voltage. So let's say I connect a battery of 2 volt here. So the channel now exists, correct? So let's say VDS equal to 0. So I have a rectangular channel, right? So now I keep on increasing VDS. So do you think the channel near the source junction is going to get affected, or the channel near the drain junction is going to get affected? Near the drain junction. And how is it going to get affected? It will become trapezoidal, then it will start to get to pinch off and so on, right? So essentially, this is going to become like this. I mean, not drawn to scale, it should not come out. Something like this. And when will the pinch off happen? When drain goes greater than 1 threshold voltage above gate. Right? So, sorry, I mean, not greater. I mean, it should be, so let's say this is 2 volt and drain volt. If we take a value, so this becomes, this voltage is 2 volt. So for what value of drain voltage are we going to have pinch off? Yeah, which is equal to not 3 volt. It will happen before that, right? So so right now, let's say when VDS is equal to 0, both drain and source are 0. This condition. So what is the sliver of the MOSFET around the gate to drain junction that it is seeing? What is the gate to channel voltage that it is seeing? That is 2 volt, right? So this is seeing 2 volt. And you only require 1 volt to get the channel on, right? So which means that it's an overkill. So now if I reduce, let's say I increase the drain voltage to 1 volt. So what is this? This now becomes 1 volt, right? So if it is 1 volt, that sliver of MOSFET which is connected to the drain junction, that is, do you think that is having channel charge or channel charge vanished? It is just going to vanish. It is at the limit. Exactly, it is at the limit. So which means that is the condition of pinch off. I increase drain voltage beyond 1 volt, then the transistor is in pinch off, or in other words, the transistor is in saturation, right? So the saturation condition in this case boils down to drain voltage. There is a minima for the drain with regards to okay, so let me put it in this way. So saturation happens when VD is greater than VG minus threshold voltage, right? So if I keep on increasing the drain voltage beyond 1 volt, in this case, the transistor is in saturation, correct? So if the drain voltage is lower than 1 volt, the transistor is in linear region, correct? So that's the only difference between the P MOSFET and the N MOSFET. In case of a P MOSFET, what was the condition? VD should be less than the threshold voltage, VG plus the threshold voltage of the PMOS. Okay, so this is the only critical difference that you need to keep in mind, the limit. Okay, everything else remains the same. So once in a linear region, so this is saturation region condition. This is saturation region condition. So once in linear region, that is, you keep on decreasing VD in case of an N MOSFET, and you keep on increasing VD in case of a P MOSFET, the equations become ISD. This is linear region, is mu P Cox W over L VSD VSG minus threshold voltage times VSD minus half VSD squared. Similarly, the equation is easy to remember because everything gets flipped. This becomes mu N Cox W over L VGS minus threshold voltage times VDS minus half VDS squared. Okay. So equations are easy to remember once you know one. That the thing that you'll have to keep in mind is the condition of the saturation and saturation and linear region boundary in case of a P MOSFET and an N MOSFET. Okay. Any questions? Okay. So, okay. So let's explain it from this perspective, right? So let's say the drain voltage has increased, right? His question was to just revisit the saturation region condition. So when does, let's say the drain to source voltage is 0, right? So let's say drain to source voltage is 0. So in that case, the channel charge is symmetric. We are okay with that? So if the channel charge is symmetric, we have enough channel charge both at the source and towards the drain terminals, which means it's in linear region. So now I'm not affecting the source, not affecting the gate voltage. I increase the drain voltage, right? So if I increase the drain voltage, this voltage difference, what is happening? Is it increasing or decreasing? That is decreasing, right? So which means the electric fields here are decreasing, right? So electric fields at the drain junction is decreasing, which means the amount of channel charge towards the drain junction will decrease. So what is the critical value of the VGD for which the channel will completely vanish? It will be equal to the threshold voltage, right? When this becomes threshold voltage, then the channel vanishes, right? That's all we are doing. That is what we are writing here. When VD becomes greater than VG minus 1 threshold voltage. Okay. Okay. So now, now that we understand these two, I mean, at least we understand the algebra between or mathematics between these equations. So the next thing to do, obviously, will be to check out how the incremental model is going to get affected. Right. So we know we are comfortable with the incremental model of the P MOSFET. We'd also like to see what will the incremental model of the N MOSFET look like. So for that, let's again sketch the incremental model of a P MOSFET. So gate source, this is drain, Y21 PSG, right? So in case of an N MOSFET, what is the Y21? So let me write the Y21 for P MOSFET also. Y21 for P MOSFET is mu P Cox W over L ESG minus threshold voltage. So what do you think the Y21 for N MOSFET will be? Yeah. Again, this is for saturation region, right? So this is probably have to demarcate. This is for sat. So now in case of so we sketch the same things, just like we sketched in case of a PMOS FET. So this will be gate. So let's say this is drain, this is source, because the current directions, we were keeping the symbols consistent with the current directions. What do you think will be the, so definitely I will have a current source here. So what should be the direction and what should be the, okay, so it should be down. Why do you say down? Drain to source. And this should be Y21 times what? It should be VGS, right? Everything is flipped. Great. So now that I have drawn this, do you think the incremental model of the PMOS and the incremental model of NMOS are any different, or they are same? No, look at it. They're identical, right? So essentially what you see is that incrementally these two devices are identical. If I give you the incremental models of both of them, you will not be able to tell whether it's a PMOSFET or an NMOSFET device. Right? The only difference comes from the quiescent conditions. The only difference comes how the biases were set up, where the current direction of the current is from drain to source or source to drain. Right? In the total current sense, in the incremental, not in the incremental model. Right? So this is good in a way. I don't have to bother about directions and all. You know, one of the incremental models, I know it's the same for the other. Right? It's one less thing to remember. So, so now couple of jargons. So, so this Y21 is essentially the Y21 of the MOSFET, right? But the nomenclature Y21 can be confusing because when we say Y21, we normally refer to Y21 of a two-port network. Now, a MOSFET can be a part of a bigger two-port network. Then when I say Y21, I always have to write Y21 of this MOSFET, Y21 of that MOSFET. That is clunky to write. So people said that we don't have to write Y21, nomenclature issue. So we'll simply call it transconductance or GM, right? So Y21 for a MOSFET is called GM. This is transconductance. So G stands for conductance and GM means conductance of a MOSFET. But when we say, I mean, instead of writing GTM, the nomenclature stuff, that we'll simply write it as GM, which refers to transconductance. So anywhere, so from now on, I'll not be writing Y21 times VGS, Y21 times VSG. It will be always GM times VGS or GM times VSG. Okay. Okay. So now let me redraw this. Let me redraw this in this format. So one more thing that people do normally, you will see I mean, if you look in the literature, this is not the usual symbol. This is not the usual way PMOSs are drawn. The usual way, one of the reasons, I mean, you must have also faced during doing the assignments, almost invariably the source in most of the cases that we have done goes to ground, right? So it becomes Y21 times V minus VG, right? So then you have to maybe flip the direction of the current source and make it positive, and all those things you have to do. So that's why generally people try to keep the directions, I mean, try to express everything in terms of VGS all the time, so that I don't have to deal with negative signs more often. Okay, so that's why the usual PMOS incremental model looks like this. Source remains source, drain remains drain, gate remains gate, no issues. But we call it in terms of GM VGS, and the direction goes up. So this is the usual one that is used for PMOS, and this is the one that is used for NMOS. Note that they are identical with regards to the flow of current, with regards to the drain and the, direction of the flow of current, expressions, everything. Just that it becomes sometimes more convenient to express things in terms of VGS or VSG, right? In terms of VGS, simply because you want to deal with positive numbers more often than not. So that's why these type of nomenclatures are used more often, right? So feel free to use any one of them as long as you are consistent, but you will see more often than not, these type of symbols are used, okay? Yes.
We assume that the source terminal is a common terminal by writing the incremental model. So in the NMOS also, this terminal is the common.
Yeah, it will be the source terminal, right? So his question is, in most cases in PMOS, we assume that the source terminal is the common terminal. Yeah, because it's a common source amplifier, right? We have been doing common source amplifier till now. So in all those cases, source used to be the common terminal. So the next thing that we are going to do is to design a common source amplifier using an NMOS, right? So then it will become clearer. Okay, so now that we have a complementary device, which essentially means that whatever we could have done with the PMOSFET, we can do with the NMOSFET, right? So then what I would like to focus on is, given that we know how to design a common source amplifier using a PMOSFET, how do I go about designing the same amplifier using an NMOSFET? I don't want to start from scratch, right? I already know how a common source amplifier using a PMOSFET works. I would like to import the existing knowledge into NMOSFET. Okay, so let's do that. So let's do the biasing first. So this was VDD, this was R2, this was R1, this is RD. Okay, so now I have a PMOS device. Sorry, this is a PMOS device. Now I have an NMOS device. This was drain, this was source, this was gate. Here this becomes drain, this becomes source, this becomes gate. The quiescent current was flowing from top to bottom. Here the quiescent current will flow from top to bottom, but from drain to source. Who was setting the quiescent current in case of a PMOSFET? Which voltage? VDD, but difference of voltages, right? VSG was setting the current, right? So I wanted to have certain amount of VSG above threshold voltage, that is the overdrive voltage. We wanted to have certain amount of overdrive voltage to set the current ISD. So who is going to set the current in case of NMOS device? VGS, right? And if we want the same overdrive voltage in both cases, how should I go about forming the VGS, getting the VGS supply, getting the VGS voltage? So I have a VDD. So what was the VSG in the circuit on the left? This VSG was how much? That was VG, not VSG, right? The voltage drop across R2 will be VDD times R2 by R1 plus R2, right? Because the voltage drop, I mean, this voltage is VDD times R1 by R1 plus R2. And we add those two up, you get VDD. Right? So the voltage drop across R2 was VDD times R2 by R1 plus R2. We want the same voltage drop in VGS in case of an NMOS transistor. Right? Then what should I do? Yeah, so same voltage divider, in place of R1, put an R2, right? This becomes R2, this becomes R1. Okay. So what about the source? So in case of a PMOSFET device, I got the gate voltage, fine. But basically I'm looking for the gate to source voltage, right? So what should be the source voltage in order to have the same source voltage with respect to the source to gate voltage in case of a PMOS? Pardon? So the question is, the source to gate voltage here is VDD times R2 by R1 plus R2, right? So I want the same gate to source voltage here. I got the gate voltage. What should be the source voltage? Ground, right? Absolute zero. So it should be ground. Okay. So the last thing to see what to do with RD. So RD in case of a PMOS was connected to drain, right? So that much we know. We have to connect RD to the drain. What about the other terminal of the RD? To VDD? Why not ground? Yeah, exactly, right? So ultimately, in this case, the current flows from a higher voltage terminal to the lower voltage terminal, right? So even if you don't bother with RD, right? Let's assume RD is not there, right? So RD, let's say, is 0. This is short circuited. In order to establish the bias, we would have connected the drain to VDD. Correct? So because the VSD in this case was VDD, the VDS in this case should have been VDD. So whatever VSD I have in case of a PMOS device, the equivalent VDS we should have in case of a NMOS device. So if we have an RD, the drain voltage is how much? ISD times RD. Correct? So what is VSD? VSD is VDD minus ISD times RD. Right? Confused? Okay, so
let's explain the transformation once again, like P in the resistor.
Okay, so you mean why the R1 and R2 got flipped?
Yes.
Okay, let's wind back 5 minutes and then come back here. So let's get rid of these guys. So what are we saying? What equivalence are we trying to draw? So we have to ensure VSG should be equal to VGS. Correct? So what is VSG in case of PMOS in whatever circuit on the left? This is VDD times R2 by R1 plus R2. Correct? Is this clear or you have a confusion here? This is clear. So we want VGS in this case to be VDD times R2 by R1 plus R2. Correct? So how do I generate that using a voltage divider? I mean, I don't want to do too much change, right? So I put, yes. The gate voltage will be VDD R1 by R1 plus R2. But VSG is what? VDD minus that voltage, isn't it? Right? Okay. So again, I mean, this voltage here is equal to this voltage. But that's not the source to gate voltage. That is the gate voltage. The source to gate voltage is VDD minus that voltage, which is VDD times R2 by R1 plus R2. So we want the same VGS in case of NMOS device, which means I essentially flip the R1 and R2. Right? I flip the R1 and R2, so I get the gate voltage in this case to be VDD R2 by R1 plus R2. So the next thing to understand what to do with the source, I mean, if the gate voltage effectively is giving me the gate to source voltage, the source can go to ground. Right? So source goes to ground. Is that clear till now? Yes, no? Okay. Okay. So now let's come to the drain side. So what should I equate? In this case, VSD should be equal to VDS, right? So in case of a PMOS, what is VSD? Source is VDD. What is drain? ISD times RD. So in case of NMOS, this should be VDD minus IDS times RD. Correct? So this voltage has to be VDD minus IDS times RD. So a current of IDS is flowing from VDD anyways. So you just put an RD in between to get that drop. Right? So
you eventually made it identical to
yeah, these two are basically siblings, right? So just the current directions are flipped. That's all. In that quiescent state. In the incremental state, as we saw, identical. Okay.
you're forcing making it identical in the
We'll see the identical model of incremental model of the common source amplifier. Next thing is to do that. Okay. So this, as far as the quiescent states are concerned, are you convinced that these two are same? Okay, fine, good. So if quiescent wise these two are same, the next thing to do is to apply input, take the output, and then do all sorts of things that we have been doing, right? So let's do that. So I'm not sketching the PMOS anymore. Which one was R2? What one? So now, in case of an PMOS, we were applying an input by coupling it through a capacitor, and we were connecting the capacitor to the gate, right? Effectively, we are trying to manufacture a VSG incrementally, right? So in this case, we would like to manufacture a VGS incrementally. So essentially, your incremental, source is already grounded, so your incremental input should directly appear at the gate, right? So now, given the last class, can you tell me what should I do? So I have a input Vi, capacitor between and the gate pointer, right? So essentially, this is what we would like to do. Right? So if the capacitor is infinitely large, then all of the sinusoidal excitation comes to the gate, right? And by virtue of putting a capacitor, I'm not tampering the quiescent points also, right? The same argument which we did with respect to the PMOS device. Okay. Okay. Now, what about the output? From where should I take the output? Yeah, we were taking the output across RD in case of a PMOS device. Here also we can take the output across RD. But the important thing to note here is that when we are talking about incremental outputs, is it necessary to take it across RD in the way I have shown, or is it okay to take only the drain voltage? Because incrementally, this voltage is not changing, right? So it is okay to take only the drain voltage also as an output, right? Okay, so that is all good. But if I again take you back to the next to yesterday's class, we said that we have a load RL which cannot be put just as a part of your main circuit. It's something else. It may be the input impedance of some other amplifier, some other stage. So you cannot use it to bias. That might have its own biasing requirements, right? So what to do now? I want the incremental V0 across RL. Again, an infinitely large capacitor, C2, right? And we saw in yesterday's class how to size these capacitors C1 and C2. So what we do, we find out the time constants with regards to the capacitor C1 and C2 and ensure that the time constants are much greater than 1 over omega naught, where omega naught is the frequency of interest that we are trying to process. Okay. Okay, so this essentially becomes a common source amplifier using a NMOSFET device. So let's do a quick incremental model of this. Assume the capacitors are shorted in the incremental domain, right? Because that's how we are going to size it anyways. So if we assume the capacitors are shorted, so let's figure out how to replace. I mean, the only thing that needs to change is the MOSFET, right? Because everything else is linear. So let's replace the MOSFET with its incremental equivalent and do a quick analysis. So this is gate, this is drain, this is source. So I replace the MOSFET with its incremental equivalent. This is gate, this is drain, this is source. This becomes GM, that is Y21 of the MOSFET times VGS. Okay. So this is as far as the MOSFET is concerned. Now we have to add all the things that are attached to it. So let's start from the gate side. So what should I connect to the gate? Yeah, definitely a VI. If I assume the capacitor to be shorted, this directly goes to the gate. What about R1 and R2? Yeah, R2 remains the same. R1 goes to? R1 also goes to ground because incrementally VDD is grounded. So essentially it becomes R1 parallel R2. Right? What happens to the source? Grounded. At the drain, what is connected? RD grounded. Then we have some capacitor C2, which again we can assume it to be shorted if we size it properly. Then RL grounded. When I say size it properly, I mean I size it in such a way that it acts as a short circuit at the signal frequencies. Right? If it's infinitely large, for example, at any non-zero frequency, it will give you a short. But for sizes of, I mean, for frequency of omega naught, we have to ensure that the time constant is large enough so that the capacitor voltage doesn't change within that one time period appreciably, right? So that's why the time constant requirement comes. We also saw with respect to Bode plot, right? With respect to the magnitude plot where we need to, why that requirement arises. Okay. Yes. Question? No. Okay. So now that we have the incremental model, finding out V0 over Vi should be easy. Can you find it on 10V? Yeah, absolute piece of cake. So source is grounded, gate is Vi. So this becomes Vi. This becomes Vi. So this current GM times Vi flows in this direction. It flows into a parallel combination of RD and RL. So V0 becomes minus GM times Vi times RD parallel RL. So your gain becomes minus GM times RD parallel RL. Right? It's identical to the PMOS device case. So if I now go back to the total circuit, so can you tell me what is the, I mean, what is the total current flowing through the transistor? The quiescent current was IDSQ, but when I applied the input Vi, what will be the total current? Plus GMVI. So plus GMVI. What will be the total voltage here at the drain? The quiescent voltage was VDD minus IDSQ times RD. what will be the total voltage? Minus that gain, right? So this will be minus GM times RD parallel RL. What will be the total voltage across RL? Yeah, so it will be minus, quiescent-wise it was 0. And this will be minus GM times RD parallel. Okay. Into VI. Yeah, correct. Thank you. So now that we know how to go about looking at currents and voltages, both in quiescent, incremental, and total. So the next thing obviously will be to figure out what will be the swing limits, right? So you bias your transistor. I mean, same thing that we did with regards to PMOS, right? So the next thing will be to figure out how to size these transistors, how to size the RD so as to, I mean, if I have 100 millivolts sin omega t, for example, then the transistor remains in saturation and so on and so forth. Okay, so I'll provide a assignment. You can take a look at it. Thank you. Yes.